So Coulomb's law is the law that relates to electromagnetic and electrostatic forces. Coulomb's law is written as F equals KQQ over D squared, where F stands for the force, and that's measured in newtons, like usual. K is a constant, it is always the same number, 9 times 10 to the 9th, or 9e9. Q represents charges, and here we have two charges acting on each other, so Q1 and Q2. The units for charges are coulombs, or the capital C. And D stands for distance, which as always is measured in meters. Don't forget to square it. That is probably the most common mistake that most students do. Another quick note is that a common term we have for charges is the charge of an electron. So the charge of an electron is 1.6 to the negative 19th. That's just a common term that you will use on many, many problems, so you need to have it written down. When using this equation to solve for any of the parts, it's beneficial to understand how it's rearranged. Obviously, if we're solving for the force, it's already rearranged to a point where we can simply plug in values and not have to do any extra algebraic functions. But if we wanted to solve for something like distance or charge, then we would have to do a little bit of algebra in order to work that out. So the first thing I'm going to show is how I would solve for distance. To solve for distance, or the denominator of any equation that you ever have, you can simply take the value from over on the equal side sign and the value that is in that denominator and trade them. This works because if you think of something simple like 10 divided by 2 gives me 5, and 10 divided by 5 gives me 2. So here I can kind of start to see this pattern that I can trade the bottom denominator number with the value on the other side of the equal sign and still have a working algebraic function. So if I wanted to solve for the distance, then I could rearrange this to where the distance squared would be K times Q, and now that force would need to take the place of the distance and end up on the bottom. Your final step using this equation would be to get rid of the square sign on that distance, so you would need to square root your answer to get the distance by itself. If I wanted to solve for the numerator, one of the Q charges on top, here I need to be able to do some algebra. So if I start back with that initial equation that we have, and we think about our algebraic processes, if I have d squared on the bottom, then the inverse of that would be to multiply by d squared on both sides. So now I would have d squared times the force equals k times q times q. So my next step would be to do the inverse of multiplying by k. Here I would divide by k on both sides to take care of that part. So now I have d squared times s divided by k gives me q times q, or q squared. So just like we had with our distance, once we have this value, I can plug in my information, take the square root of the answer, and that would give me my value for q. So we have three methods that we can solve for. We can solve using our basic method, or where it's more of a plug-and-chug style, where I have my values and I'm finding the force. We could solve for the distance, or we can solve for the charges. So let's take a look at a couple of example problems where we would use these terms. A Van de Graaff is a device that we can use to create electrostatic forces. On a Van de Graaff, the charges are going to build up on the sphere and then pass to whatever touches it. In this case, the charges are all going to be similar in charge. So we have a bunch of electrons passing from the Van de Graaff to the person. Remember, electrons are the only things that move in terms of the atom. So I've got all these electrons spreading out, pushing against each other, repelling each other, trying to spread out, so people's hair tends to stand on end and look really crazy. So because we have all electrons trying to spread out or repel, we get that hair-raising experience. Now, if we wanted to apply a little bit of math to this idea, we could find the electrostatic force, or the F, that would be needed to separate two strands of hair by 0.09 meters, which would represent our distance. So going back to those equations we just formed, if I wanted to find the force, then we would need to know K, our two Q's, and our distance squared. K is a constant, 9 times 10 to the 9th. Q is the charge, and in this case, like we mentioned, our charges are electrons. Well, the charge of one electron is 1.6 to the negative 19. If I have two strands of hair, each with the same charge, then I would write it as 1.6 to the negative 19 again. Or I could write it as 9 times 10 to the 9th and 1.6 to the negative 19th squared, because 1.6 times 1.6, both to the negative 19th, is the same as squaring that function. In my denominator, I would have 0.09, and it does need to be squared. Now I'm ready to just plug it in my calculator and come up with an answer. I would suggest putting my calculator into scientific notation, which can be done using the second functions for most calculators. If you're following along and wanting to check your work, then you should come up with 2.84 times 10 to the negative 26. Common errors would include forgetting to square that denominator, or forgetting to square the Q, or forgetting that 9e9. So just be careful that you have all the components together. But you should come up with this. The units for that force would be newtons, as with every other force. So the next example that we're going to do is going to be an example where we are solving for how far a charge would go. In this case, we're solving for distance. Recall from what we did earlier with rearranging that equation, I'm trading the force and the distance, my denominator, with the value opposite of the equal sign. So I can start with my equation looking d squared with the f on the bottom, and my k, q, and q still on the top. So we want to know how far. We have 9 times 10 to the 9th as a constant value. Now we need our two charges. It says for a charge to jump from a cloud with the charge of an electron. So my cloud has that charge of 1.6 e to the negative 19 coulombs. Down to a tree with a charge of 2 times 10 to the negative 15th coulombs. So those will be my two charges, my electron as well as my tree. On the bottom, I will place my force, or the value that is being measured in newtons. Because I've already done the algebra previously with how to solve and rearrange, again I'm left with this problem that I simply plug into the calculator and let it work out. So I come up with d squared, so plugging all this information into the calculator, d squared equaling 2.55 times 10 to the 6th. Now obviously I don't want d squared, I want just d, so I'm going to take the square root of that value in order to be able to come up with my final answer, which I get as 1.596 to the 3rd, or written in standard notation, 1,596, and these would be distances, so in either case I would want to measure in meters. The final example that we're going to be using is to determine how much charge. In this case, we are solving for Q. We have two identical balloons, and because we have two identical balloons, we're going to end up with Q times Q, or Q squared, in our equation. They experience a force of 5 times 10 to the negative 25th newtons, and they are 0.75 meters apart, which would be our distance. So what we solved for earlier was that we could do our force times that distance squared, dividing by that K constant, or Coulomb's constant, would get us Q squared, or the charge squared. So in my calculator, I'm going to do 5 times 10 to the negative 25th times my distance squared, divided by my K constant of 9 times 10 to the 9th. When I hit equals, that's going to give me Q squared. So I'm going to want to make sure that my last step will be to take the square root of whatever answer I get. So for Q squared, I come up with 3.125 times 10 to the negative 35. And when I take the square root of that value, I find that the charge of my balloons would be 5.59 or 5.6 times 10 to the negative 18, because this is a charge measured in coulombs, or capital C. So here we worked an example of all 3 different types of algebraic methods that we might have to work. If you understood the backing for the slide where we came up with these kind of quick equations, then that's a great thing to have. Otherwise, you could do the algebraic functions as you've learned step by step from your math class, and you should still be able to come up with these final answers.